The next talk is by Mustafa Bal from Harvard University. He'll be giving us a talk on DéjàVu, bringing black box security analytics to the cloud. There's a small error in the program. This paper actually has 3 authors, and the third author, Mustafa Bal, will be giving the talk. And an important thing to note is that this is one of the few papers where an undergraduate student has been involved as a researcher, and Mustafa is an undergraduate student giving a talk today.
Thank you. Yes. Thank God. Awesome. Sorry for the wait, guys. So, hello, my name is Mustafa Bal. I'm a fourth-year undergraduate student at Harvard University. This is the project that I worked on at IBM Research last summer of 2017, with my mentor Shripad and my manager John Turk, both at IBM TJ Watson Research Center. And my project's name is DéjàVu, bringing black box security analytics to the cloud. So we're first going to talk about the rise and the evolution of containers and how they're applied in industry. And then we're going to talk about some of the challenges and the opportunities that containers offer. And then we're going to transition into the motivations for our project, and then show some results, experimental conclusions, and then, yeah. So containers as a concept and as a product are a fairly new innovation, and over time they've gotten a lot more acceptance and they've gotten a lot more usage in industry. So Google themselves say on their own Google Cloud website, from Gmail to YouTube to search, everything at Google runs in containers. So if Google supports it, then I think there's significant support for the usage of containers in industry. And the good thing about containers is that containers provide consistent and predictable environments that are isolated from other applications. And they are pretty small, and they can be run with a low overhead. And we want to keep them small and keep them with a low overhead. And we know that there are good automated container orchestration platforms such as Kubernetes that exist. And with using those, we can build some pretty powerful platforms. And like I said before, as there are a lot more applications that are being used by containers every day, the support for that will just get better and better as time goes on. And but the thing is, containers are less secure than virtual machines. And the reasons for that is, number one, containers use basically the system level APIs, whereas virtual machines use hypervisor visualization APIs. So VMs are more secure. And a good example for this that I found was VMs, securing a virtual machine is like securing a single house. They're pretty popular in the United States, where people are living their own villa, their own house. And if someone, if your neighbor is basically, if someone comes to your neighbor's house and robs their house, that does not really affect your own house's security, because your house is not in any way connected to your neighbor's house. Whereas securing containers is like securing your apartment, your suite in an apartment. If someone breaks into your neighbor's apartment, that's a problem for you, because, well, all that bad guy has to do is just go in through your own door. And Docker as a platform kind of forces the user to leave their front door open, not the most outside door that keeps everyone outside of the apartment, but it kind of forces you to leave your own front door open. So as a result, virtual machines are more secure than containers. But so they do provide some challenges, and they also provide some opportunities. First of all, with containers, with the traditional approach, we can't really install multiple applications in a container. A container is supposed to do one thing, and it's supposed to run one application. If, let's say, in one container, you're running an antivirus software, you don't want to also run MySQL on it. And the thing is, with a single machine, with a single computer, there may be hundreds, if not thousands, of Docker containers or just containers running on it. And as a result, these containers need to be scaling up or down very, very quickly. You can't afford we need to minimize the overhead that results from these containers. We can't afford to lose any more time just instantiating or destroying these containers. However, containers do provide a good level of separation and a good level of separation from like the base platform itself. So you can run applications that do completely different things in a separate way, like they're supposed to, and you can decouple basically like the monitor, such as like an antivirus, from the monitored, such as like the data that's going in and out of the computer. And as time goes on, there's a growing trend to offload data monitoring from data generation, which we're going to talk about now. So before, when there used to be security applications done on collected data, those processes weren't that complicated. You were just going through the data, making sure there were no, like you would set some like hard code values to be scanned for, and if you saw those, then that would be a problem. But now these days, people are doing machine learning on the data that you collect. People are doing all sorts of different things that require additional hardware, such as a GPU. So what the trend now is, the trend is that you separate your data collection and your security analytics, so that a machine that, let's say, has a GPU or 2 or 3 can most effectively do its security analytics. If it's like GPU intensive, it can benefit off of that and not not put additional load on the main machine. And again, it provides separation of concerns and overheads. So it makes sure that, or it helps you separate what you collect and what you analyze. But however, a problem with this is there are a lot of security applications that have been built already that are designed to run locally on the machine that you're trying to secure. It's sort of like, again, installing antivirus on your own computer. If you install antivirus on your own computer, that antivirus will scan your own computer. You can't install that antivirus software on a different computer and then expect it to scan your own computer. But we still want to utilize these existing security applications. We don't want to just get rid of them just because they don't support this. Yeah. So then our motivation is clear. And before I go to this, actually, I would like to point out that there exist these crawlers that can go through Docker containers and sort of get a scan of what the Docker container is. So what the processes are running, what files exist, what the details of the OS are. And the crawler can sort of see all this data and collect it in a text file. And so with that, we have also done preliminary analysis on like these security applications, and we found that these applications almost never write anything. Like they never call write Linux commands. They only do reading. The way that these security applications run their checks is that they just read through the data you already have. The two reads that exist here, I don't know if my mouse is moving, but at the very bottom on the column modify for OpenSCAP, which is a open source security analytics software, you see that there were 3 calls made for write. Those are just for logs. So the write operations made are not necessary operations. They're just for the process itself to take note of what it looked at. And so what we offer here is that, like with our DéjàVu platform, instead of rewriting security solutions to work from data, we find a way to reuse existing security solutions as black box analytics in the cloud. And in other words, we basically simulate our container environment and run the security applications on a dedicated analytics machine. And to do this, we have developed our own, most of my internship was dedicated to developing our own file system user space version, Confuse. And we've also utilized the file federation software overlay. What Confuse basically does is it goes through what we call the frame data here, which is the data that we've collected from the container that, again, as I mentioned previously, details everything that exists on a given container. And it provides this given data to the container file system user space. And it builds a virtual version, basically, of this container. And with this virtual version, we can send and collect data from like the standard Linux utility functions. And so when we run a security application with our Confuse, right below our Linux utilities and right above our frame data, we can simulate our container, and we can kind of trick the software, we can trick the security software into thinking that it's actually running on the actual machine that it's, checking for its security, rather than on a simulated Alex machine, which is exactly the case. Yes, and we only had to implement, surprisingly, 7 read-only read functions, read standard Linux functions, instead of the many other functions that also exist, because we found those were the only functions that these security applications are using. Yeah. So we have an example. We have a sample security application here called CHK Rootkit, which basically checks for rootkits that exist on your system. So here we have Confuse, which is again going through the previously collected data that we have and building a virtual terminal interactive version of the container. So just by going through this .text file here, one can do ls etc, and it will show hosts and password, and one can do all sorts of these Linux commands. And now we also add our folders that we've manually created. So the chk rootkit run folder here contains the packages that chk rootkit requires to run. So for each security application that we're integrating into our system, we need to also provide the package that it needs to run with. And Workspace is just a place where these security applications can do write commands in. And Federated is where we'll be collecting all these folders that exist into one specific folder. And we do that with overlay. So now, once we use overlay to integrate our Confuse and our chk run and our Workspace folders, we get the folder /mount/federated, where once you do overlay /mount/federated on a terminal, you basically get, you basically trick the computer into thinking, well, if I do ls space /, it gives you this result right here. So it simulates these folders all together, to be all together, and which helps the security application to thinking, well, I'm running on the machine itself, not on a separate analytics machine. Yeah. And we're running out of time, so just to go quickly through some of the data collected. On the left here, we have some of the more popular Docker applications that people use, and the millisecond file creation time here is the time it took, let's say, for Ubuntu and for CentOS 7 to manually be built on the machine itself. So let's say CentOS 7 took 39,000 milliseconds. The total time that it took for our platform to build, to quote unquote build its version is 23,000 milliseconds. For Ubuntu, the difference is a lot greater, like 9 milliseconds versus 13,000. Yes, and yeah, on the left here we have like a log graph, log scale graph, where we are comparing building and running these Linux commands on like the native machine itself, where we allow it to use its cache and where we don't allow it to use its cache. And we also have tested the performance of these applications and these Linux utility functions on the vanilla version of the file system user space and with our modified version of file system user space. And I just want to quickly point out your attention to the PS function here. The reason why ours takes a lot longer than all the others is that in our own file system, we're doing a lot of repetitive parsing. And so there are a lot of symbolic links that need to be looked at. And so far, our implementation is just that it looks at each of the listed symbolic links, and it goes through these files. Yes, and just to quickly add, here, this is the coverage percent of our platform. For OpenSCAP, we have achieved a coverage percent of 84%. What this means is 84% of the time, we can show you exactly what it would normally take to, what it would normally show on the machine itself. Whereas for, let's say, CHK Rootkit, it's 100% coverage. So you get the exact same output as if you would get if you were to run the platform on itself. So in conclusion, we recognize that security of cloud containers is now more important than ever, and that it is smart to decouple data collection from security analytics. The way we approached our solution is that we made data accessible to traditional software by mimicking the system over itself, or the system itself over the data. And as a result, we enable traditional security applications, legacy security applications, to run unmodified in a black box fashion. And yeah, that's it. Thank you for your time.
Do you have a rough idea of what, like one of your results, it was a really big performance difference between the CentOS and Ubuntu? Do you have some intuition for why there's such a difference in those cases?
Yeah. Yes, actually. So I would like to go back here one sec. Yeah. So the exact functions that are being called when you're building Ubuntu, when you're building CentOS 7, are obviously different. And this actually ties back to the graphs that we have here, the microbench evaluations, where there are just these certain functions here, such as read link, as you see here on the right, that takes a lot longer on our own Confused platform than even the native or the vanilla version of the file system user space. The reason why this takes so long is that this was not the main focus of our project, basically, and that reading the symbolic links did not add much to making sure that these security applications run well. So we just wanted to show the performance testing on the most popular container applications. And so we thought that showing the difference between showing Ubuntu's build time and the CentOS build time, they can be different based on the exact file system functions they're calling. Yeah. So there just needs to be more work done to further optimize, let's say, the read link file system call.
Yeah. So thank you, everyone. Let's